Hello, dear students. We now have to see Vinylogy and isosterism. We are seeing methods of how to modify a prototype in a qualitative way, in a visual way. That is, what we are seeing are criteria that you have to develop to be able to modify. And it says, the point of introduction of multiple links or vinylogy consists of view, transforming a simple link to be into a double link or a triple link. When one does that within a structure, the lipophilia of the compound does not change drastically, because we are not, if the original number of atoms is the same, altering the chemical composition drastically. But if the geometry is drastically altered, we go from having a sd3 hybrid to a sd2 hybrid. We go from having a tetrahedral structure to a structure. As the sd2 geometry is called, planar trigonal. That is, we go from having links angles of 109.5 to having links angles of 120. Question: and why does the rigidity increase when introducing double links? Double links are not rotable. There is no free rotation around the double link, and in addition, if another extra complication is introduced sometimes when you have a double link, it is potentially generated geometric isomerism. What is the geometric isomerism called? It is not R and S. It has another name. Let's see when we have, for example, a structure of this type versus cis-trans. It can already be cis-trans, or it can also be EZ. Of course, those terms are used more as our Germanic terms E and Z. The E would be the equivalent to trans, and the Z would be equivalent. Example: let's consider the design of stradiol hormonal analogs. What we have here on the left is the stradiol molecule. What is the stradiol? There it says natural estrogen, but what is that? Biologically speaking, a hormone. Very well. The female sexual hormone par excellence, and we have the presence of an aromatic ring that can make perfect type interactions with the estrogen receptor. And in fact it does. We already have the rest. A fairly lipophilic structure, cyclopentanide type, derived from phenanthrene, and two polar groups that are important for anchoring the estrogen receptors because they make hydrogen bridge interactions. Now it has been determined that these two hydroxyl groups are important, and the distance between them is relevant. This distance from one hydroxyl to another is relevant. If you eliminate the hydroxyls, the activity drops considerably. This is a high or low lipophilic molecule. Low or high? How many carbons did you manage to solubilize a hydroxyl? Around 3. And here, there are many more than 6 carbons. This has many carbons. It is a high. The nuclear receptors, or estrogen receptors, are nuclear receptors. Therefore, the molecules that act on them are usually very lipophilic molecules, natural or synthetic molecules, as we are going to show below. With this information, someone said we could create a new molecule that preserves this distance between two polar hydroxyls. That is a good question. We could measure it. I am going to leave loading a program in the meantime so that you can see how one can measure this in a quite reasonable way. So it is good that you consult me we are going to open the program. Well, while it loads, next, we have a derivative that was created in order to imitate the natural estradiol, the female sexual hormone, and we have that it is a cis-diethylsteal, that's how it's called. And it's inactive when we say cis, it was E or Z. Exactly, perfect. But here, next to it, we have the isosterism. And this one is active because it preserves this geometry with these distances between the hydroxyl groups. And not only that, but we have the aromatic ring that we already know, is going to do p-stacking type interactions with the receptor. Question. And if instead of being hydroxyls, we had fluoride atoms here instead of hydroxyl? There are two questions. First, if the fluor can be a hydrogen bridge, and the answer is yes. Only as an acceptor. Then we would have to see if in the receptor these hydroxyls are acting as additives or acceptors. If we put fluor, the fluor will only be able to act as an acceptor. But fluoride hydroxyl is often in medical chemistry a change that one seeks, a change that one makes. That replacement is used a lot in medical chemistry, and this type of replacement receives the name of isosterism, which is what we are going to see a couple of days later. So there I am going to advance so that you can develop criteria on how to modify something to potentially achieve something better. Now, the other thing that would change when adding fluor instead of hydroxyl is that the molecule becomes more or less electrophilic and exactly increases the electrophilia of the compound. The aromatic rings become more electrodivergent. Well then, if now we overlap the two molecules, this is obviously a simple two-dimensional overlap, but it illustrates quite well that there is a similar distance between the hydroxyls, both of the hormone, as of the natural synthetic derivative. Why do I say that it is synthetic? How can I conclude so quickly that the trans of opionis, the 2-stilbestrol, is synthetic? Because it is a simple molecule, and because it is also tremendously symmetrical. It is rare that a natural compound has a perfect symmetry. That is a molecule too simple. And with a plane of symmetry, it is rare in nature. Cells, things are always. So now we have here a new molecule that I do not know if you notice the change when I pass from the hour. Structure. As we draw it in the program to the minimized structure, small change. It moved the substitutes to minimize the repulsion. What do you think happened? That is, how does this process occur? Largely, I do not want technical aspects. But what happens in an energy minimization? I think that some idea they happening. What was done behind the scenes to reach a more optimized structure? Geometrically speaking, what can you tell me about this process? See how interesting. As the double link, you see it here. There is the double link, how a chain moves to one side, the other to the other side, and the benzene rings in this arrangement. What happens are calculations with equations, basically with the Newton's laws. The Newton's laws underlying this, considering the molecules as if they were formed by spheres connected by springs, and in that way the best minimization is achieved by classical mechanics. This is a quick minimization method. This was not a quantum calculation. If not, we would have to wait much longer. Well, let's go here to what the question was. We take the hydroxyl here and the beta. Let's see. There is one 12.7, quite close, 12.07 angstrom. Then with this type of tool, you will be able to get further, not only because you can measure things, but also because in this interface, you will be able to overlap molecules and vary and substitute. One can propose something new in a rational way. There is where the chemical eye matters a lot. Then, for example, if you would like to overlap this with respect to the original to see what changed, the distance in the length of the phenols was more or less 3.5. The distance for a hydrogen bridge of a complete phenol. We can also measure it. Probably, of course, at this moment, I do not remember the value, but let's measure it from this carbon. It would be up to here for the complete phenol, 4.164.2, approximately, and we also have that the molecule can be seen in another way. We can see it in this arrangement, little more realistic, to see the surface then. This is super rigid. This is not raw. That double link in the impossible center, that it is rot or not true, a representation of this type. Then with this, we are going to move a lot to be able to see interactions, linking the and to be able to propose new things from our Kusa equations. Very well now. Then, the underlying principle of inserting double links says that two substitutes X and Y joined by a vinylic chain or polyvinylinica, call it a double link, or several double conjugated links, or for example, a double link and an aromatic ring, behave as if they were joined directly. We can explain that in terms of the resonance or molecular orbital electronic theory, and that the effects of the attractor groups and data are transmitted by superposition of pi orbitals. In large part, what is being said is that in random molecule, we have two groups, for example, a group A and a group B, where one group is negative electron and the other is positive electron. If we allow there is an electronic conjugation from here to here, then we favor that polarization necessary for activity, as long as here in the center we have a system that allows the flow of electrons from one part of the molecule to the other part of the molecule. As electrons flow through the molecule, precisely a strategy is through the resonance. The electrons move from one place to another. Then here is aliphatic vinylogy, where X and Y are important groups for activity. One electropositive, another negative electron. Well, if in between we insert a double link or several double links, that polarization is preserved. Suppose that X is the electropositive and Y is the negative electron. Then what does this mean with a double link? The effect is preserved, or with several double links. And here, if you insert an aromatic ring, question is preserved in all cases. For example, if X is the electropositive group, we have that here, not certain effect goes to Y. And if it is in para, also not certain, it is preserved. And if there is a double link and double link substitute, we also have the resonance preserved conjugation. Watch the Of course, it will depend on the substitutes, and to analyze it case by case. A case later, and the other question would be good. And what happens if we have another type of combination, for example, this aromatic ring connected with the X and with the Y like this? Or instead of having such a simple aromatic ring, you have, for example, another aromatic. We could have, for example, an X here and an Y here, that you can tell me those two cases. Then, in the first case, the resonance distribution is preserved no, because there is no conjugation. Then there is no resonance conjugation. I cannot reach resonance. 2. Why impossible? Okay. And in the second case, remember that this sulfur participates in the resonance, contributes to the aromatics with one of its electronic pairs. And if I try to draw the resonance from X to Y, I do not arrive. There is no way it is going to reach this position here. That is, if I was here, yes, but not here, so be very careful. I do not have a way of injecting electrons to Y, so be very careful, as it is out there. It very close, uncle. We are uncould be no. A question can only be generated in this case, in this resonance, in an ortho position and ortho position. Exactly clear, that is an ortho position and a para position in an aromatic ring of benzene. In methanol, no, the Vinylogy does not serve us, because there is no electronic conjugation there. We want is to preserve the electronic conjugation of a group with another when we know important groups for activity. When the ring is more rare, you will have to determine it with a resonance analysis. Okay, then this may be a case, but there may be many other unusual rings then. What happens here? 3 examples in one says, and third. Electronic density of the critical centers for activity. In the first case, we have an ester, where an oxygen is electropositive and the other electronegative. In the 3 cases, it is preserved. Because here, when inserting the double link, we have the conjugation. And if we insert a in para, it is also preserved, that distribution of charge. But if it was in meta, in the last case, here in meta, no, there it is lost then. In these cases, the density is preserved now, are being altered with this, the length of the molecule, therefore that we also have to analyze if it is going to be good or bad. Sometimes, by altering the length, a lot the activity. Yes, it is the same analysis. For example, if you had a blue aunt, we would have this. Example, because we place a here, is here and there. We cannot this position. It is occupied, I have here, and here. Well, if it is here, it is a case if we are going to have an electronic conjugation, and if it is here, they are safe, for example. So there and also then, they have to do it case by case, since the conjugation, they have to analyze the case by case in more complicated. So, to remember a little bit of reasoning. Well, here, there is a notable case, and I find that with this a brutal molecular simplification is achieved. This is the superposition of cocaine and procaine. Observe the following in black is. Cocaine has a type of asa bicycle system, connected by an ester to the benzene ring. Cocaine, in the esa bicycle portion, also has another ester, but which is not relevant for local anesthetic activity. That are these. These anesthetics are inhibitors of the neurosodium channels. They are inhibitors of the sodium channels, and in that way, through conduction of the nervous impulse in the neuronal axons. Well, and in red is the molecular of procaine that is much simpler. It is nothing more than an aniline with an ester and with a diethylamine ethyl chain. then it is a very simple molecule, but that preserves what? Thing preserves the distance of this nitrogen to a polar group connected to a hermetic ring. Then there is a great structural similarity. That is why I have them superposed. So how the pharmacophore has been preserved. That is, if you want to create a new local anesthetic, you have to respect this pharmacophore, an aromatic ring, a polar group that can something else, and finally, a basic tertiary nitrogen atom. Well, this has been studied, and it has been determined that in the case of the procaine and its congeners, to achieve the maximum inhibition of the sodium channels is convenient a group of this type in position for a group type. This is an aniline. It is a strong resonance electrode, and it is contributing to the electronic density of this oxygen. That is delta minus, and the nitrogen is delta. Plus, if we have an electrode in position for right here in this position, the inhibitor effect is maximized because we have a powerful hydrogen bridge acceptor. In this position, if we eliminate this nitrogen, the activity is not completely lost, but it is reduced. In fact, the cocaine was not that group, but it has activity, as in this local psycho. Then, with a group of now, the activity is maximum. And for example, these derivatives have been created. It is preserved by inserting this link. Very well, the molecule is rigid and allows the conjugation. But if you insert their own line, a simple link, there is no conjugation, and the activity is lost. That is so drastic, that with the simple link, the activity is going to be lost also. If you place a type derivative as, they are called two rings of benzeno, attached biphenyl. Very well, we have a biphenyl. The complete conjugation is also preserved through that long and extensive system. So, we also have that it is active. It is active in this type derivative biphenyl, in that consists of basically then the Vinylogy that is different from the homology. Homology is to insert simply carbon with the sigma link. Vinylogy is to insert the double links that allow the conjugation. By resonance, there are cases where the activity has been lost because it is drastically altered, or, well, the geometry or the distance affecting. In that way, the interaction acid, antituberculosis. What is tuberculosis? What causes tuberculosis? Exactly. The bacil of coho is a bacteria. Then this is an antibacterial. A double link was inserted between the ring of how this ring is called. And out there goes pyridine. Well, the pyridine is important for the activity, as well as this carbonyl group, and the double link is the distance is drastically altered, and the activity is lost. The conjugation is between the entire system, between the carbonyl electrode, in fact, the nitrogen of the pyridine. That is what is the electrode or the attractor. Exact, that nitrogen is the attractor. Good, but the alteration of the distance between the polar group and the ring makes the activity as antibacterial. And we come to our final part of all these strategies to modify that are basically a range of concepts. And finally, we are going to talk about isosterism and bio-isosterism. Is usually today is talked about isosterism. We talk about bio when we get the same. Biological activity. I will clarify those terms, but the bio prefix is nothing more to make this distinction that we get the same biological activity. We are approaching the concept because it is a somewhat abstract concept. It says that they are bio, and they are isosterous. Sorry, the classic definition says they are isosterous atoms or groups of atoms. Then there we have two things it is. A lax concept. It is not a specific concept. Atoms or groups of atoms, large associations with it. The same properties and electronic behavior that is super ambiguous, because it says the same properties. What properties? The same electronic behavior. What type of electron can be of many types we are going here? We are going to approach first by the classic criterion, which is a rigid criteria. The concept of classic isosterism is a non-pharmacological concept. It has nothing to do with the design of drugs. Well, the classic criterion is based strictly on electronic criteria, and it was defined by Langmuir, who said that they are isosterous molecules. Then here we are, talking about the complete entity molecules that have the same amount of atoms and the same amount of electrons of valence. That is, we are going to have isosterous molecules, for example. And since it is a rigid concept, it will only serve for very specific things. These are not drugs. These are gases. Then we have the molecular nitrogen versus the carbon monoxide, molecule, the same amount of atoms. Of course, two atoms in both cases, the same amount of electrons of valence. How many electrons of valence we have in total? We would already have 6, 7, 8, 9, 10. Very well, 10 electrons of valence. In both cases, 10 the second is polarized. It already has loads. It does not matter. It does not matter polarized, because the concept continues to be fulfilled. The carbon monoxide is quite reactive, precisely because of this polarization. And because this polarization makes it reactive, they see with a little anomalous here in this structure, this new structure of molecular, but it is a resonant structure, if you want to call it. That explains well why it is reactive. There is already the carbon atom and the oxygen, and in which they see something strange here. Oxygen is positive clear, and that makes it super reactive very well. That is, the carbon mon is a strong electrophile that can be attacked by a nucleophile in such a way that oxygen recovers its stability in terms of low density, and is united, for example, in a covalent way to the hemoglobin of the blood, causing damage, and also electron transporter chain that they have in common. These two molecules, curiously, those two molecules have in common a similar density, constant dielectric, similar solubility in water, etc. They are molecules with super similar physical properties here. There are only examples. Z the fusion points, the close ones that are, and the points of ebullition also, tremendously similar, because they are isosterous. And then it is a broad concept. It is a concept a little strange. They do not have that with isobar or isotope, not to be confused. Please, they have a similar chemical behavior. We go to the other side now. The definition serves us for drug design. Here we expanded with the non-classical definition. And how are we going to define isosterous? There are several ways to do it. Example, we could define isosterous. Nothing else down here. When two functional groups are of similar polarity. Example, if you have a molecule N with a group or H in this position, we are going to say that is similar to if you have another similar group connected there, for example, IH2. Now you see, but that is very different. One is a base, the other not. Yes, but the two provide polarity and solubility in considerable water. Then both are groups and isosterous. There are differences, of course, yes. What happens if it is protonated? There drastically. But if it is a non-protonable nitrogen, there it resembles more, because alcohol protonable. Then ideally, if this mine is not protonable, it would be a good isosterous polarity of the hydroxyl. We go up here, geometry, okay, when two groups have similar hybridizations. Similar link, English, similar sites example. Let's say we have this, it will seem maybe a little strange, this example, a ring with an oxygen group and something else. Well, here next we could have as isosterous of that ether a carbon with two atoms of oxy, fluor, and then R generate a similar geometry because the hybridization of oxygen and carbon is CP3. Very similar link angles, and in size, they are similar, although they do turns out that fluor is very close to which atom? In size to hydrogen. And we are going to explain later that this type of substitution also imitates the behavior of the two electronic pairs of oxygen, because in the case of oxygen, do not forget that it has two pairs of electrons. Exactly, and here the carbon does not have electronic pairs, but instead of electronic pairs that it has, fluor then, here I can receive two hydrogen bridges here too, but through the criteria of sex fluors I understand the idea in CF2, fluoromethylane, is an ether isosterous as strange as it seems. Then, as you can see, a fairly lax concept, we could have isosterous that provide solubility. Similar to a molecule that has two groups, for example, polar, that generate a similar solubility. Could also be of solubility in the lipid medium, if that is also a good expansion. To the concept example, it is very common that if we have a molecule with an halogen as a chlorine, a molecule, any with a halogen as a chlorine, that will be very similar to and bromine. And with iodine, it moves away because with iodine, it moves away a little. The lipophilia of the system is very similar because with iodine, it would move away a little more from the contribution that chlorine makes in that. It is different from iodine to chlorine, and there is some exactly, and the size of the iodine is much larger very well, and that generates physical and chemical in the properties another, we could say, by acidity, and there is a question that we will soon answer. I can replace an acid group by another acid group. Example, you can replace it, a carboxylic acid, by another acid group, such as a sulfate acid group, are very similar. The two release proton to pH 7. That proton is going to release pH 7, and the molecule that charge is going to have. If it releases the proton negative in both cases, we generate an anion. Now down there is A. Question, it is already a question. A little deeper, from the point of view of reactivity, that is why. There is no isosterism of bases, there is no isosterism of basicity in medical chemistry, and there is the question is why we are seeing that we can replace an acid function by another acid function. Well, what happens in the case of basicity? You can replace a basic function by exactly it is. Very difficult at the medical level for the following: the base par excellence exact, the base par excellence is nitrogen. What else can be protonated as a nitrogen does in midwinter? Practically nothing. That proton capture is very difficult to get, you will say. But there we are, similar to nitrogen, as for example, a phosphor. Well, the truth is that there are very few drugs with phosphorus. Phosphorus is toxic, and apart from that, phosphorus is not protonated, only in when a phosphorus can protonate in very rare organic bases. Look, I am going to show it here, because it is a very interesting organic base. It's and they sell them. They sell them on websites, and providers of reactives because they are strong. Organic bases we have shown it is not true, and so that it will not be forgotten anymore to see where this was. As it is a super complicated structure, there is the protonable phosphorus, but because it has protonation capacity, because it has a resonance stabilization, but incredible. That is, these three nitrogens are stabilized by resonance, and the one below, also the molecule folds completely, like these plastic expandable balls that are toys for children. And that is why that phosphorus would be an exception if it is called a base of Berkadis, and the one that is below, if it is called a Cusadat, although there, in that case, it is a nitrogen that is protonated in nothing more than a bridge for resonance. But here it is the nitrogen, that in this case the one of Berkadis is rare. A protonable phosphorus atom, a superbase, not ionic to see the third. Pegasus is around 30, which is super basic. And capacity to form hydrogen bridges, then it also allows to form or generate a isosterous example, something very punctual we were just seeing. Let's say that we have a carbonate that can be a hydrogen bridge acceptor. We can replace it with any other carbonate type function that has something in. Elsewhere here, for example, an ester, an ether, etc. There is still an oxygen capable of oxygen being a hydrogen bridge acceptor. Or we could have that can be replaced by a function of this type. Then here I am going to put R, and we preserve one of the hydrogen bridge as it is called. This function from here. Be careful, amine is when the nitrogen is sp3, and this has a double link here. Amide is when there is nitrogen carbonyl, that is, if for example here the X were nitrogen, that would be an amide, but this with the double link is an iminate, exactly. It also says carbon dioxide as a hydrogen bridge acceptor. Then the butyrogen bridges can generate isosterism, and with that we can generate a pharmacy just by changing small functional groups. We are going to see an application exercise. Look, it says fluoride and hydroxyl. They are similar in their properties. They have a different number of atoms. Let's see here in the center. Fluoride and hydroxyl are two rings, are two hard rings, are two high hardness rings. In different amounts of atoms, that is when I say that they are hard, and that they are not polarizable, very little polarizable, because they are small, but they have in common the same amount of electrons of valence. How many electrons of valence? 8 electrons of valence in each case. They have a similarity in their chemical properties. In the same way, if we expand these ideas, we can say that these are atoms, and they are hysterical, but we already know that it is very to replace nitrogen, because phosphorus adds toxicity to the compound arsenic even more. Formerly, there were drugs with arsenic that were antibiotics, but they were stopped using for obvious purposes. Andification. Also a positive nitrogen would be isosterous of a positive phosphorus. Oxygen, and electronic isosterous of sulfur and selenium. There are almost no drugs with selenium, because this is also a metalloid, and it translates into toxicity, but oxygen and sulfur isosterous in angular capacity in electronic pairs, but differ in something gain. Oxygen and sulfur, in what they differ? To see the two cases, we already have to be in the same group. But the sulfur is much greater. than the oxygen, and metabolically, do not forget never that the sulfurs are sometimes allergenic, and on the other hand, the sulfurs are also oxidable. That is, this sulfur that you see there can be oxidized to sulfide with it already metabolically. Then there could be a problem. The sulfur is susceptible to oxidation in the body. If well, we also have this. Small table called the green table that shows us isoelectronic groups. That is, they are columns of groups that are isosterous, nothing more than because they have the same amount of electrons. Valence. It is a fairly limited concept, but it is to show some things such as that if suddenly you have a nitrogen that is not protonable electronically, it can be replaced by its equivalent GH oxygen, could be replaced by an NH or CH2. I insist in the case of G nitrogens. Whenever it is not protonable, if we go from something neutral to something drastically changing its properties, a fluor can be replaced by an H by an Na2. Not protonable, or by a methyl, they are similar in that. In the amount of electrons in size, they are also similar, and this last one is nothing more than the reference table, because we obviously have that type of groupings in a farm. In a liquid sulfur, an atom of neon, that is not going to be true in a farm very well perfect. We are going here to the amplifications that Erlenmeyer made about this concept, and it was found that there are other groups that have no correlation in terms of amount of valence, electrons, or even size as we saw just now, but they are very similar. For example, pseudo-halogens chlorine cyanide, thiocyanate. They are very similar to each other. There may be drugs with cyanide in the stream. The truth is that if there is already, that is, if you have a drug that has a chlorine, something similar there. Could not be another halogen, could be a cyanide, a CN. And if there are drugs, particularly, there are antidiabetic drugs that have that group within the structure. It be metabolically stable, except that it is not cut. That, nor is it released to the plasma. Toxic. Not true. The cyanide and thiocyanate is also an isosteric group. Previous ones, on the other hand, as the sulfur is large. It has been seen that an isoster of sulfur, and this one is rare, so these are the examples that you have to remember. A sulfur can be replaced by a double bond. That is, an atom can be replaced by two carbon atoms with the double bond. That would explain, for example, this is down here to the right. It says isos. In fact, the sulfur is, or rather the complete thiocyanate that is here. This thiocyanate is very similar to benzene, in that, in size, the two rings are very similar in size, and the sulfur is also a little, let's say, so polarizable. The electronic pair of the resonance is very delivered. The two are tremendously aromatic of the series of three. That is, when we have sulfur with oxygen and nitrogen, the most aromatic of all is with sulfur. If they are looking to replace benzene for something that is very similar in the concept of aromaticity, the most aromatic is the thiophene, and the least aromatic is the furan. The furan is the least aromatic of the series. In fact, the furan is a ring a little strange. In fact, it is quite reactive in some cases. It is well polar. Also, the furan, as well as the dog next to it, is the least aromatic. So if I am looking for a strong pistachio, I will not think about this as my first choice. I would have to think, if I cannot put benzene, I would have to put a thiophene. If I am looking for an effective pistachio, because this, well, and see how curious then. a sulfur that was more or less the same size and properties of aromaticity than two carbon atoms we go here, and that finally leads us to this other ring equivalence. We go here, where the first case says a benzene and a pyridine, what criteria is being applied there? Nothing more than the NH criterion, the same amount of valence electrons. Equal to here, oxygen, sulfur, equal amount of valence electrons, oxygen, H equal amount of valence electrons. Now here, be careful that these would be isosterous in the amount of valence electrons, but the first is only an acceptor of hydrogen bridge, and the second question is an acceptor and a giver, or only a giver. Very well, the pyrrole is only a giver. Giver of proton cannot accept because it cannot act as an acceptor. Of course, that is not true. It's because that is super dislocated in the internal resonance of the ring. But the oxygen to say the same, but that the oxygen has two, then it will always have to be able to act as an acceptor of hydrogen bridge. Very well. And we go to the last examples. 16. Non-classical criteria and polarity isosterism. Here we refer to polarity isosterism. We refer to the fact that we need to have, for example, a negative electron atom, delta minus, that is polarized, for example, by resonance. That is, we have a carbonyl. The question is, why can I replace the carbonyl that maintains this polarity towards oxygen by any other derived from carbonyl? The first case would be an ester. An ester unculat would be the one that follows amida. Very well. And this one, how is it called? Nitrila. Now, the one that has the negative polarity here is the nitrogen, but ask already has the polarity, but they are angular, isosterous. No, there no longer applies the concept of angular. Is only polarity isosterism. But in terms of angle, they are very different. So if this acted at a specific angle, receiving a hydrogen bridge, perhaps this is lost, because now it has a linear geometry. And if we cannot replace by another carbonyl, we need to place another different group a little bigger. We would have the cases down here. Because bigger, because it has sulfur, then we would have that instead of carbonyl. How is this? Function of this is not a carbonyl, because it is a sulfur and mercury. That is already sulfide, and be careful, because the carbonyl and sulfide are polarity isosterous. But again, they are not isosterous. For example, of hybridization, the carbonyl is St2 trigonal plane. The angle is, how much is the angle? Be careful, 120, 120. The sulfide does not have 120 because very well, the sulfide is sp3. There is an electronic pair that is not drawn. There is sp3 that suffers, and therefore the angle in that case is distorted. It will be close to 109, but not the same value. Most likely less than 109. When there are too many electronic pairs contract, and we are going to the next one here, next to the one that is here, next to what it is. This is no longer sulfide, it already has two. So it has another name. There is no problem, of course. It is not sulfide, but it would be sulfone. And there in the sulfone, it is evident that this is tetrahedral sp3, and it is tetrahedral. As the next one, if the previous one was sulfonan, and this has an amino here, this is a sulfonamide. And all of that then are isosterous polarity. sulfonamide seprotona F7. Generates positive charge. Nitrogen has an electronic pair, but the answer is no, because oxygens are very powerful electric attractors by impossible resonance. In fact, sulfonamides. When the group R is an electronic attractor, sulfonamides lose this proton and mate. Can be isosterous of what group that delivers proton? Of a carboxylic acid. Exactly, it would be isosterous very well of carboxylic acid, an electric attractor that at least makes the pegasus of that proton come to be close to 5. These here are the isosterous groups, that is, these three that are here are similar to each other. Those that are there, they are the names. The first one says Uncle urea because it is not urea properly. It would be urea, so instead of sulfur outside, careful, urea is with oxygen. And if it was oxygen, it would be urea. But since there is a sulfur Uncle urea, the second cyanoguanidine, now someone will say, why bother to place a cyanonitrile group? Because it is synonymous. Or why bother in this other case to put a nitrile group? Why not? Simply we are saying that they are isosterous already in all these groups. Why not simply 4? Example. I am going to draw here, instead of a CN, or instead of a nitro, simply a proton, that is. Smaller is simpler. There is atomic economy there then. If we have a proton and here, I have GH2. Is not true a proton from the point of view of the size. It even looks more like each other. These two, because placing these groups so exotic, okay, the cyanonitrile group and the nitro group. That was here, because they had to place, remember, that this is our game, the category question, the Uncle urea, that you can tell me about this fragment, enough neutral or positive. Yes, it is like an oxygen. Enough neutral very well, because the electronic pair of this is in resonance, and that of the other is also in resonance towards sulfur. Then very carefully, the urea or urea are always neutral to pH. If you instead have this, or like this, and here we have the guanidine function alone, and the guanidine function has pK sub 12, that is, this would be protonated, and here it would no longer be guanidine, okay, it would be an aminocetane, and in this case this aminocetane with the double bond could also be protonated in some of the nitrogens to avoid exactly to avoid that nitrile and nitro are placed, since they are electro and electroattractors very well, electroattractor and electroattractor, and they are so electroattractors. In fact, they are two of the most electroattractor groups that exist. They have what is called a superpositive Hammett constant. Sigma is the Hammett constant, and that we are going to study in Kuzar. We are going to occupy, they are one of the most electroattractors groups, that there are so much so that they steal the basicity completely from the functional group to which you connect it then. If you connect nitro or nitrile to a basic group, the basicity completely disappears. And then that is the reason why we had those groups there. And if only what interests us is the size to replace a group similar to another by size, we have several examples there. The first case, hydrogen similar to fluor, are the only two that are similar in size to the entire periodic table. They remember the values we had seen. The values, some point of atomic radius, when we saw the halogen bridge, when we saw intermolecular interactions. I do not know where I have here intermolecular interactions. At some point we mentioned the radii here. Of course, there we have the difference that there is a 35% difference in size R. The only two that are similar in angstrom, of course, 1.06 and 1.4 angstrom of atomic radius. And it is good to suddenly see that type of values. It helps to dimension things, so we could replace a methyl by a trifluoromethane, that then they are similar in size. And here we have this group. We could replace an oxygen by a CF2, not only because they are similar in size, but because both are acceptors of hydrogen bridge. Remember what we had mentioned this. Oxygen has two electronic pairs that can accept hydrogen bridge, and carbon has two fluids that can also accept hydrogen bridge. Is like the fluids are substituting very well, of course, exactly. That is why they are isosterous, both in size and in acceptor capacity of hydro. And then some small examples of application. The case of ibuprofen and flurbiprofen. Everyone has taken ibuprofen once in their life. It is an anise. It is an antifebrile. The only thing that was done here was first all this group that is down here to see how all this is called and very well. Then we have a group there of isobutyl type. It has 4 carbon atoms, a ramified group. And by size, it became something a little bigger but compacted. As it is another benzene ring, directly then, we have an isosterism, not zeta, and not only that, in the other, that are similar, and then this was replaced from here, that it was a hydrogen by the atom of flux to increase the C electrophilia, and that it has a better electronic link to the oxygenase cycle that are inhibited by this type of structure. That is, whenever you see molecules of this type derived from this acid, this is a propanoic acid because it has 3 carbons, 1, 2, and 3. Derived from propanoic acid, they are inhibitors of the oxygenase cycle, they are ions, they are anti-inflammatory, non-steroidal. In the case of the fluoropropheno, I assure you that it has a better IC50, therefore an IC50. Higher or lower, very well, and IC50 lower, excellent in. Not all are in the market, some are withdrawing from the market. And so there are many ions, there is one that was withdrawn, for example, that was selective by the oxygenase cycle 2, that was the calcite. I remember the name at this time, the rofcoxyl. The rofcoxyl came to the market. It was selective by the oxygenase cycle 2, therefore it did not produce ulcer, but it produced heart damage. Clearly, it had to be removed because there were serious cases. It is very good. It is very effective for strong pain. In reality, technically, it is when there is expression of the clear and the oxygenase cycle 2 is expressed in chronic inflammatory processes. It is expression of the oxygenase cycle 2. There, they will not be so effective, since it would be, for example, I ask myself with the hammer then, there is no time for all of major isoforms of oxygenase cycle 2. Of course, there would be a simple aspirin. It is a chronic process. It is a very good example of a chronic perfect look. And now here an isosterism based on acidity, and here we have need is a group that can deliver a proton and therefore remain with a negative pH 7 net load. That is, I need at least something that is as acidic as a carboxylic acid that has a pH of a similar to 5. And we have all these rare groups In the first case, we have a sulfuric acid that releases the proton. We are marking the acid proton. The latter, as long as the I is electronegative. If the R is electronegative, this R group, from here, the proton comes out as this group was sulfonamide. Well, sulfonamide. Perfect here. We have another example where there are two protons. That is, hydroxylamide. What do you think what happens there which could be the most acidic atom of R? The structure and why. Remember that when the proton is delivered, it is going to generate a negative net load. And from there you have to ask yourself, and said net negative load, there is a possibility that it stabilizes it in some way. Exactly. That will generate an extra stabilization, that is, as we have an electric attractor, it stabilizes. The anion and the anion, when it is formed, also stabilizes by resonance to the carbonic. So there are two factors. If the amide does not have the H for no reason, it loses proton. The amides are neutral. Remember that they are neutral. They do not protonate, and down here are the most exotic cases of isosterism that you will find. Be very careful, because when one sees a ring, one does tend to think that a ring is going to ionize. We have triazole. This is triazole. Therefore, how is it called the one that follows if it is good tetraazole perfect? This is a hydroxy because it has an O group and soxazole, as it is called the ring of six, with a single oxygen. Is similar, but what happens is that here, the oxygen, of course, when if there is another carbon fiber, it would be a quinona very well. But very well. This is a pyranodihydro in this particular case. This pyrano has a carbon, and the electric attractor has an O. That is electronegative, and therefore, that proton of the O is the acid proton. And the negative charge, how it is stabilized? Well, there the truth is that resonance is not so clear, because the charge is that one traces the resonance from here into the there. This thing I have no way of reaching the carbon. But if we can say inductive effect increases the acidity, the same as this oxygen from down here, there is here in isoxazole, which is the acid proton, also the H in the tetraazole, the proton of the NHN there. Some in the triazole. So they are quite rare cases, you will say here, to complicate our lives if, with a carboxylic acid, it is enough and well, because it turns out that sometimes additional interactions are sought. I explain with a carboxylic acid, you neon, that can be an acceptor of hydrogen bridge. That other interaction can be the carbox. Very well then, with a carboxylate, we have those two possibilities. With the carboxylate, we can make a hydrogen bridge as an acceptor saline bridge. But there is something that I cannot do, and that the first three can do it exactly. The first three that are here. These first three, the last one, not because this different is no longer as aromatic as the others, despite the fact that if this oxygen delivers the electron, can make a strong start here. So yes, not yet. We could try and see what happens if, of course, with the tryptophan. Of course. If not, if it could be, but the only thing is that connecting, that instead of an acid is added. An additional synthetic complication of all means of all the attempts could be made, of course. Then there we have the rarest groups. I think that would be the strangest thing you are going to see of isosterism. There is the explanation why they are acidic I. Those rings never protonate, those deprotonaterimine, with a negative charge that stabilizes by resonance, so be latter thinking that they are bases that are going to protonate because they do not have, they are only acid nitrogen, rings acid, so do not confuse. And this is the last thing to say, that when we have certain groups that form hydrogen bridges, we can replace them by other groups, similar in geometry, capable of forming hydrogen bridges. The first case that we have here is a simple ring that can be both a donor as a hydrogen acceptor, and this type of systems that is common in certain types of drugs is called, where the exact concept came from, for example, which catecholamine you know, dopamine, norepinephrine, and then they were like that. For example, norepinephrine had dopamine. It would be up to there. Exactly with the hydroxylochiral, it was norepinephrine. It is a catecholamine. Very well then, see that this is how it is called. And there's already, with the exact benzimidazole, because it also has two nitrogens, two atoms capable of accepting, or at least hydrogen bridge. Do not forget that this proton that is there is a customeric proton. Exactly by proton transfer. It can be down or up, it jumps from one side to the other. This system is also the same as semiquinonic. So to speak, it also has two hydrogen bridge acceptors, the same in this last case, the nitrogen. This is a lactam, which is what is a cyclic amide with the other. Oh, within the structure. Well, to conclude only now, deliver this concept that says bio and isosterism, because bio, where did bio come from? Well, it says there the two form bio and sosteros are those compounds that fulfill some of the definitions of sosterism, and have the same type of biological activity, that the biological activity is preserved. Another definition says groups or molecules that have similar physical and chemical properties and that produce approximately similar physiological effects. That is, we already look like the effect, although not necessarily the same then. There we talk about bio and sosterism when a group is changed by another and the biological effect is preserved, or it is similar. Well, we just saw a particular case of isobutyl with benzene. They would become bio and sosteros because they have similar lipophilia properties and generate a similar biological effect. So there is nothing in more than refining the term of a question of concept. This is already then question. In the first case, they was isosterism is altered some drastic property of the molecule, as for example, the basicity. I am asking for this first example. The basicity of the compound is altered by making this subtle change very well, because it is not altered. Exactly the first case is not protonable. In fact, what is the name of the nitrogen function connected to a double link? Is no longer only amine okay. That is not a common in current mind, because the double link causes it to lose its basicity. And not only that, all this ring is an nitrogens here, we have this carbonyl. This is super electric attractor. The double link there in amine. So that is not basic, and therefore there is an electronic isosterism where nitrogen is changed by TEH similar lipophilia. In both cases, obviously the one on the right is a little more lipophilic. When having key instead of nitrogen, second example, procane. Exact oxygen and nitrogen are similar in size. If they are similar in size, they are from the same period. Now someone will say, but one is an acceptor of hydrogen bridge, the other is a donor technically speaking. But this is not the important group. We just saw that the important group in local anesthetics is this. That is the important one. That is the important acceptor. In addition, in the case of this nitrogen, this is not protonable. It is an amida, okay. An ester, the other difference. This is an asterism exactly. This is an asterism, so that one of the two is more stable metabolically, which is more stable, very well, the procane amida exact. The procane amida is much more stable than the procane, because the esters break more rapidly metabolically speaking than the amides. The amides break slowly. We are now going to this anticonvulsive. We have two. There first it says oxazolidinadione versus hydrogens only. An oxygen by an end generates a change in the basicity of the compound, and neither because the nitrogen here is inside a type structure, urea cyclical, okay. As there is another oxygen, it is called idantuan. It is not protonable. This oxygen then has a size and polarity properties similar to the other, so they are isosterous. Let's go. Yes, of course. If it is not relevant, there is no problem. But if here now, instead of having an acceptor, we have a donor, and that alters everything, of course it would not serve interaction with the target. Suppose that in the target, there is that it was very relevant, and there is, for example, a tyrosine. If there is a tyrosine problem, because if there is a tyrosine, there we would have to see if it can be adapted in such a way that the tyrosine remains, so that there it can be the hydrogen bridge, but as a donor instead of an acceptor. We would have, but at the moment they are electronic isosterous, and they are also bioisosterous. Yes, of course, this link is rotatable. This link is rotatable, of course. In theory, of course, it should not affect drastically. You have to do the analysis very well. When the link is rigid, less chances of accommodation. Next example, we have a cyclical base. What is called this type of bases that are part of genetic material of anti-neoplastic pharmaceuticals are these two rings, and this is a pyrimidine A. Imidazole the function in the whole system is that it is one, and there's a hydroxyl above, but the system at the base is a purine. The purine. We have the pyrimidine and imidazole system, the whole purine cycle. Well, this purine, already called hypoxanthine, is changed to hydroxyl by ester on the side is zymacaptopurine. Then also isosterous of, in this case, is isosterous, angular isosterous of no polarity, but not in size. Already remember that the sulfur is considerably larger. Which of the two will have greater metabolization? The sulfur, because the sulfur, we already see that it oxidizes nepathically intensely, that if it is going to have greater oxidative metabolism, zymacaptopurine is that if isosterous. To the left is the uracil, good. That is not a drug, okay. The uracil is not a right, is the 5-fluorosil. What type of ice? A proton perfect size. And because the one on the right is a drug at some point in the past. We made a mention of this, maybe a little fast superficial, but this simple change. Because the uracil is a nitrogen base to synthesize and the halogen bridge is with the vacuum, and the flare does not make halogen bridge already, but look at the thing. That is what happens at the uracil, apart from the fact that it is synthesized uracil from the uracil. It is created timina, because there is an enzyme that cuts here, and position it places methyl. And so we have timina that is necessary for the synthesis of adenine, and this other initiates that process, because we had said in the past that this process of cutting and sticking a methyl group here was impossible. Therefore, this is an inhibitor of the synthesis of adenine, because it is impossible, because we cannot cut and stick a methyl in this case here. Because we cannot cut the carbon fluorine link, that link is very strong. Energetically, it is a strong link, it is a high energy link. It will not be cut enzymatically. It will not happen, it will stay united, and therefore inhibits the enzyme in a competitive way, and we maintain based on acidity. Here it is, when X is a simple carboxylic acid, that is an ane, we have an ane that is a derivative of carboxylic acid in this position here. What was the acid proton oxametazine? There are two protons, but what is the acid? Well, that would be the acid proton. Third, how is this cycle? Perfect tetrazole releases the acid proton. And in the three cases, we have that they are equivalent anti-inflammatory. Functions are preserved. It is very important to have an acid function to have an NAD.